In this last section of Chapter 3, we're going to collect a couple of theorems that are really important regarding continuous functions. And along the way, we'll prove some of the facts about the behavior of a function with respect to the derivatives that we've been using up to this point. We just haven't proven them rigorously. But before we begin, I need to introduce a special type of hyperreal number. We've used hyperreal numbers throughout the semester, but one thing we haven't talked about is what would be a hyperinteger. Now we've got integers. We know what integers are in the reals, right? 1, 2, 3, 4, 5, 6, 0, -1, -2, -3, so on. We know an integer when we find one in the reals, but what about in the infinite sets? If we go off to infinity, we should have a similar concept of numbers that are 1 unit away. You know, if we write them in sequence, each one would be 1 unit away from each other, whether we're in the negatives or the positives. So we should have some sense of what a hyperpositive integer would be and what a negative hyperinteger would be. Well, to get a handle on that, like how do we formally define it? We can just say they exist, but how do we know when we have one? We have to use the integer function. So if you'll recall, the greatest integer function is the value that if I put a number in, so this is for real numbers, that's how we defined it, that if we put a real number in, it'll give us the integer that is just below it, right? So the greatest integer of 3/2 would be, well, the integer just below that is 1, whereas the greatest integer of -3/2, the integer just below it would be -2. Right? So this function just gives the integer that is just below. Well, from the extension principle of for hyperreal numbers, we know that that we can take this function, this greatest integer function, and extend it to the hyperreals. That I should also, this is also defined that if I put a hyperreal number into this function, it should give me a value. And so let's take a look at what the graph should look like. And it would look something like this, where we know its behavior with values that are real, right? That any number between 0 and 1 gets mapped to 0. Any number between 1 and 2 would get mapped to the value 1. Between 2 and 3 would get mapped to the value 2, so on and so forth. So that's what it should look like in terms of real numbers. But then if we zoom out and look at the hyperreals, well, this also has the same behavior, that it continues on in the step progression, and similar would happen if we zoomed into the negatives. So we can give a definition using the greatest integer function for what a hyperinteger would be. And so formally, a hyperinteger is any hyperreal number y. So any number y such that y is equal to the greatest integer for any hyperreal, for some hyperreal x. So we can put all of the hyperreal numbers into the greatest integer function and it returns some value. The output is always an integer, or in this case, since we're extending this up to the hyperreals, the output would be a hyperinteger number. So that's all we mean by integer. It's going to have all the characteristics. If we add two hyperintegers together, right? If say h and k are hyperintegers, and I'll denote hyperintegers with the integer sign, but with a star. So it could be a regular integer or it could be some infinite integer. Nonetheless, if h and k, then if I add them together, h plus k would be a hyperinteger. So we can have arithmetic and algebra that all stays the same, that the behavior of these infinite integers will be just the same as regular integers. Okay, this kind of seemed to maybe come out of left field. Why do we care about these hyperintegers? Well, they're going to be important for defining partitions, infinite partitions. So let's first off talk about what a finite partition would be. So if I have, say, the numbers, let's just take the number line, let's say from A to B. And if I wanted to break this into, so let's divide into, I don't know, 5 parts. So I want to cut this up into 5 even pieces. Well, how long should each piece be? Well, it would have to be the length, let's call it delta, would be b minus a over 5. So let's give these real numbers. So let's say this is 2, and maybe this is 10. I can easily turn that into a 10. So here I'm talking about 10 minus 2, and I'm going to divide it into 5 equal pieces. So that would be 8/5. So each one would be 8/5 length, and so this would be 2 plus 8/5. Then this plus another 8/5, so 2 plus 2 times 8/5. Then into another piece, it would be 2 plus 3 times 8/5. And I didn't do this quite well, but then finally this would be 2 plus 4 times 8/5. And the last end piece, which is 10, which is equal to 2 plus 5 times 8/5. And so I've partitioned this, again, I didn't draw into scale, but I can partition this into 5 equal subintervals. Right? So I can do this, and these are all of equal length. They all have the same length, and they've cut my domain A to B, or in this case 2 to 10, into 5 equally spaced intervals. I know my picture doesn't look equally spaced because I didn't draw to scale, my apologies, but imagine, if you will, right, this distance is 8/5, this distance is 8/5, so on and so forth. So in general, if I want to take a partition from, again, I'll draw it again. If I want to take a partition or take an interval from A to B and divide it into n equal pieces or intervals, then my adding factor, I'm going to see my pattern here. It's 2 plus my delta, 2 plus 2 times delta. So my delta will always equal b minus a over n, where n's an integer, right? So I would say the partition is given by these intervals, a to a plus delta to a to 2 plus delta, so on and so on until I get to the very last interval, which would be a plus n minus 1 delta, and then b. And how do I know the endpoint is b? Well, b from up here, we know that we could solve this, that b is equal to a plus n delta. So the very last piece is my b. So these would be my n partitions of the interval. Okay, that's a finite partition, right? N is some finite number, like up here, n was 5. I cut it into 5 equal pieces, or it could be 27, or it could be 2 million. Any of those numbers, though, are finite integers. What if, on the other hand, I want to cut it into an infinite number of intervals? So what if h is an infinite integer? So I want to cut my domain into this many pieces, but it's an infinite number. So again, I've got my interval, or my domain. I'm going from A to B, and now I want to cut it into an infinite. So what would my delta be? What would be the length of each of my interval? Well, just like before, delta would be the length of my domain, so b minus a, and I'm going to cut it into h pieces, so h equal pieces. And of course this means we could solve for what b, just like we did before. The endpoint is equal to a plus h delta. And using that, then what would be my intervals? Well, it's not going to look too terribly different from before, but it would be given by a to a plus delta to a plus 2 delta, exactly the same as before. And then we go all the way up to a plus h minus 1 times delta up to b. This is my last interval. Now, there's no way I could graph this. I couldn't mark this out on a line because there's an infinite number. But we've still mathematically defined what an infinite partition is. All right, so that's an infinite partition. I'm going to put that on the back burner for right now. We're going to look at some key theorems, and these infinite partitions will show up in their proofs. We're going to need this as a machine to prove some things. We're also going to see infinite intervals come up in the next chapter regarding integrals. And so they're going to come back. They're a very useful idea of taking some finite interval, a to b, say, and cutting it up into an infinite number of pieces. This is a common approach in calculus. This is our first time kind of thinking about it, but that doesn't mean it doesn't show up often.